Having considered the mechanism of imine formation and imine hydrolysis, we now turn our attention towards secondary amines. What happens when an aldehyde or ketone reacts with a secondary amine? Well, the answer is that we form a structure called an enamine. Okay, so given on the screen is a typical reaction between an aldehyde and a secondary amine. In this case, it would be dimethylamine. And the product is called an enamine, and that should make sense because, as you can see, it's a functional group containing both an alkene and an amine, where one of the alkene carbons has the amine nitrogen coming off of it. And then, as we will see, water is a byproduct of this reaction, just like water is a byproduct of the imine formation reaction. So this may be a new reaction, but you actually know 80% of it already. The first 4 steps of the mechanism are exactly the same as that of imine formation with a primary amine, except we're going to use a secondary amine instead. So I'm going to go through this quickly because you've already watched the video on imines. The first step is the nucleophilic attack of the amine on the carbonyl carbon. Now, of course, in this case, it's a secondary amine rather than a primary amine, but same idea. And then the second step is the exact same intramolecular proton transfer to give the carbanolamine. Now we don't have a hydrogen on that carbanolamine, but other than that, it is exactly the same as the mechanism that we saw for imine formation. Same goes for step 3. Protonation of the oxygen to make a good leaving group. So the carbanolamine is still not something that's stable. It's still going to want to lose water. And the way we have to lose water is to protonate that oxygen. Note that this reaction is also happening under weakly acidic conditions. So in addition to having dimethylamine present, we have a reasonable concentration of dimethyl ammonium present also. It is this that serves as the acid to protonate the OH. Once again, everything that we talked about in the context of imine formation applies here too. Can it protonate on the nitrogen? Yes. Will it protonate on the nitrogen? Yes. Will that get us anywhere? No. So it is the small percentage of molecules that protonate on the oxygen that can then move forward. And then moving forward implies that that leaving group is going to leave. So we lose water as a leaving group. And we once again generate the iminium ion. Okay, so the resident stabilized carbocation. Now, in this case, note that the iminium ion has no hydrogens on the nitrogen. In the case of imine formation, we had a hydrogen on the nitrogen. In this case, we do not. And that's going to dictate the difference in the final step of the mechanism. So step 5 now is going to be deprotonation of the iminium ion on carbon rather than on nitrogen, because you can't deprotonate it on nitrogen to give the neutral enamine. Okay, so it turns out that the hydrogen that is acidic in this case is the hydrogen on the carbon next to the CN double bond carbon. And we call that a beta hydrogen. So if you don't have any beta hydrogens, you cannot form an enamine. So we need to have a beta hydrogen, and luckily I started with a molecule that does have a beta hydrogen. I didn't draw that beta hydrogen in explicitly until this final step because I didn't want you to start thinking about it before you needed to. But now you need to start thinking about it. So here's what happens. Another molecule of dimethylamine comes in. It is serving as a base in this reaction. It is a strong enough base to remove this unusually acidic hydrogen. Okay, so that hydrogen gets plucked off, and that's the first arrow. Now, the electrons that are left behind instead of staying on the carbon, which is the way we've always drawn acid-base reactions before, we actually use those electrons now to form a carbon-carbon pi bond. So we're going to form a carbon-carbon double bond here from a single bond. And then if you are adding a bond to the C double bond N, to the iminium carbon, you also have to break a bond from that carbon. The bond that we're going to want to break is a pi bond, because as we've discussed, pi bonds are weaker than sigma bonds, and we don't have a leaving group to expel. But that CN pi bond is really going to want to break because that nitrogen has a positive charge on it. So if we break the CN pi bond and put the electrons onto the nitrogen, we are eliminating the positive charge, and we end up with the neutral enamine. Okay, so let's look at this a little bit big picture again. We know that primary amines form imines and secondary amines form enamines, and we've already looked at the fact that the difference lies in the last step. Just going to show you one more example in which case you have a ketone, and the ketone's going to have hydrogens that are capable of being removed in the final step. So if you have a primary amine, the last intermediate you end up with, the iminium ion, has a hydrogen on nitrogen. That's what gets removed by the second molecule of amine in a proton transfer step to generate the imine. With a secondary amine, your iminium ion in the final step does not have a hydrogen on the nitrogen, so we remove a hydrogen from carbon. We remove one of those beta hydrogens, and that leads us to the enamine. Okay, so imines are formed when there is a more acidic NH to remove. Enamines are formed when there is no NH. And enamines could hypothetically form from primary amines. There is no intrinsic reason why the beta hydrogen could not be removed in the top case, but that would involve removal of the less acidic hydrogen. The NH is going to be more acidic than the CH because it's a hydrogen bound to a more electronegative element. Okay, so that's enamine formation, and then in the next video we will consider the reverse reaction of this, which is enamine hydrolysis under strongly acidic conditions.